Hello, my name is Juan Cruz Ayoroa, and I'm the co-founder of SimNet. Welcome back to our two-part video series on mastering airfoil selection for fixed-wing drones. In our previous video, we covered the basics of how airfoils work and discussed how their geometry influences their aerodynamic properties. So today I want to share some practical strategies and tips to help you pick the most suitable airfoil for your next fixed-wing drone design. So let's get started.
Subscribe to our channel so you don't miss our upcoming series of videos where we'll show how you can design and optimize your own fixed-wing aircraft using SimNet Designer. We'll show you how to use the Fusion 360 CAD software for detailed structural design and demonstrate how to create a flyable prototype using 3D printing. For this video, our goal is to find the best airfoil for a small fixed-wing unmanned aerial vehicle designed for long-range cargo transfer. The aircraft has a wingspan of 1.5 meters, a wing chord of 20 centimeters, and an expected cruise speed of 15 meters per second. We'll study two main approaches to find the best airfoil. The first one consists of a qualitative methodology where we compare and contrast candidate airfoils based on key performance metrics. After this, we'll look at a quantitative approach using the SimNet Designer software tool. Next, we'll examine frequently used airfoil series and explore commonly used airfoils for different types of aircraft. Finally, I'll provide other tools and resources that can help you find and select airfoils. Let's begin by exploring a qualitative method we can use to find the best airfoil for our fixed-wing aircraft design. For this methodology, we'll first look at the literature to identify a few candidate airfoils depending on our aircraft's characteristics, and obtain their geometries and aerodynamic coefficients. From this data, we'll extract 6 key parameters for each airfoil, which summarize their characteristics and can be easily linked to their effect on the performance of the aircraft. Finally, we'll compare the airfoils using key parameters to find the best one. In section 3 and 4 of the video, we'll delve into how to identify good candidate airfoils depending on your aircraft design, and how to obtain their aerodynamic coefficients for each one. Once you have identified the candidates, you will obtain their geometry and aerodynamic data. As discussed in our last video, the aerodynamic characteristics of an airfoil are described by their lift-to-drag ratio, and moment coefficients, which are a function of angle of attack and Reynolds number. For this analysis, we'll focus on a single Reynolds number that captures the cruise operating conditions of our aircraft. Recall the Reynolds number equation. You can obtain the air density and dynamic viscosity from a Google search, based on the expected atmospheric temperature. Plugging in these values, along with the aircraft's cruise speed and wing chord, we obtain that the Reynolds number will be around 200,000. Here are the aerodynamic coefficient graphs for the average Reynolds. Now we can extract a few key metrics from these graphs. From the lift coefficient curve, we can extract the maximum lift coefficient, called CLmax. This measures the maximum lift provided by an airfoil before it enters stall condition. Secondly, we can look at the shape of the stall curve. As discussed on the previous video, some airfoils feature sharp stall curves, while others have more gradual drop-off. From the drag coefficient curve, we can extract the minimum drag coefficient, or CD-min, which measures how much drag the airfoil generates. From the lift-to-drag ratio curve, we can extract the maximum lift-to-drag ratio of the airfoil, or L over D max. L over D max measures the maximum aerodynamic efficiency of the airfoil. The moment coefficient at zero angle of attack, or CM0, is a measure of the magnitude of the pitching moment generated by the airfoil. Additionally, flatter and more constant CM curves improve pitch stability and control. Finally, we can look at the airfoil shape itself. As we will see, we also need to consider how the geometry affects the structural integrity and manufacturability of the wing. So in summary, the 6 main parameters are the maximum lift coefficient, minimum drag coefficient, maximum lift to drag ratio, the moment coefficient at zero angle of attack, the stall behavior, and the airfoil geometry itself. Let's study how each of these parameters affect the overall performance of the aircraft. Understanding this will allow us to judge which airfoil is most suitable for our design. The maximum lift coefficient measures the amount of lift an airfoil can generate before it stalls. Airfoils with a higher CLmax allow the aircraft to carry heavier payloads and reduce its minimum speed, also known as stall speed. The minimum drag coefficient measures how much drag the airfoil generates. Therefore, airfoils with lower CD-min will allow the aircraft to fly faster. The maximum lift to drag ratio measures the aerodynamic efficiency of the airfoil. Higher L over D max will increase the aircraft's flight range and endurance, as well as improve its glide ratio. The moment coefficient measures the magnitude of the pitching moment, and therefore the amount of trim drag needed for the airfoil. The shape of the stall curve indicates how predictable a stall is. Generally, a gradual stall curve is preferable because it offers more forgiving characteristics, allowing pilots to better anticipate and manage the stall when it occurs. Finally, we must look at the airfoil shape itself to determine its adequacy in terms of manufacturability and structural integrity. Depending on the manufacturing techniques and materials, some airfoil shapes may be more desirable than others. Let's now apply this methodology to our baseline example. Based on the literature, two good candidates for high-lift, low Reynolds airfoils are the Selig 1223 and the FX 63137. We will use Simnet to look at the two airfoils side by side and compare their performance using the 6 key metrics. First of all, we look at the geometry and the implications it could have in terms of manufacturing and structural integrity. The Selig 1223 has a very thin trailing edge, which would help reduce the weight of the wing, but could also lead to a weak structure and more difficulty in adding ailerons. Next, let's look at the maximum lift coefficient. The Selig 1223 offers 40% higher maximum lift coefficient, which is a critical benefit since our design is intended for heavy lift purposes. Both airfoils exhibit a gradual stall, although the stall for the FX 63137 is more lenient. Looking at the minimum drag coefficient, both airfoils offer a similar minimum drag, but the FX 63137 maintains a lower drag over a higher angle of attack ratio. Since our design is not meant for high-speed cruise, the increased drag of the Selig 1 and 223 is not a big penalty, as it allows for an increased maximum lift coefficient. Looking at the maximum lift to drag ratio, if we design the aircraft to cruise having the wing at around 5 degrees angle of attack, the efficiency of the FX 63137 can be around 26% higher than the Selig 1223, which could provide a significant boost in flight range and flight time. Finally, looking at the moment coefficient curve, we see that both require similar trim at zero angle of attack, but the moment coefficient of the FX 63137 is more constant with angle of attacks, which can help improve the pitch stability and control of the aircraft. The main takeaways are that the Selig 1223 provides 40% higher lift coefficient, while the FX 63137 can provide 26% better efficiency, along with slightly better stall characteristics, manufacturability, and a flatter moment curve. For these reasons, we will choose FX 63137 as our airfoil. While the previous method offers a qualitative evaluation of an airfoil's impact on aircraft performance, a quantitative analysis approach can yield more definitive and optimized results. This method begins with selecting an airfoil from a database, utilizing its properties to compute the aircraft's complete aerodynamic profile. This includes calculating the wing's aerodynamics based on its geometry and chosen airfoil, as well as considering the lift and drag generated by other aircraft components like the fuselage and structural elements. Subsequent steps involve evaluating the performance of the aircraft with different airfoils to identify the most effective option. Calculating the aircraft's aerodynamic properties and overall performance can be a complex process. While for simple aircraft designs this process can be done through hand calculations, more typically, software tools are required to conduct this analysis accurately. Here we will show an analysis using SimNet Designer cloud-based drone design and analysis platform. SimNet uses fast algorithms to predict the aerodynamics and overall performance of the aircraft based on the airfoil selection on real time. Here we have used SimNet's trade study pane to explore how the performance of our baseline design changes as we change the airfoil of the wing from among over 100 airfoils from the database. In this graph, each point represents a different airfoil selection, allowing us to compare each design in terms of the maximum flight range in the y-axis and the maximum vehicle weight on the x-axis. Since our aircraft is a cargo plane, we want to find a design that achieves both high range and high payload capacity. In other words, airfoils which approach the upper right corner of this plot. Therefore, we can identify this area as poorly performing airfoils and this area as good performing options. The series of airfoils that lie on the top right edge of the dataset are what's called the Pareto optimal front. All airfoils in this curve are optimal. From this plot, we can also get an idea of how impactful the airfoil selection can be on the range and payload capacity of the aircraft. The impact on the maximum range is on the order of 30%, while that on the maximum weight is on the order of 9% in this case. Here is where the Selig 1223 and FX 63137 airfoils lie. As we can see, they are near the optimal, so our qualitative analysis methodology was effective. As expected, the FX 63137 provides better range performance due to its higher lift-to-drag ratio, while the Selig 1223 provides higher lift capability due to its higher maximum lift coefficient. However, the trade study was able to identify more efficient airfoils. Looking at the optimal airfoils in the Pareto front, those that provide highest range tend to be thin, cambered airfoils. Being thin allows them to reduce drag and increase range. However, this may complicate the manufacturing and structural considerations. Airfoils that provide better lift performance tend to be thicker and have a flatter bottom. At this point, it's a good idea to take a deeper look at the Pareto optimal airfoils using the previously presented qualitative analysis to identify possible issues or benefits of each airfoil that can be found when looking at their aerodynamic coefficients directly. Based on this analysis, we will choose the DAE21 airfoil, which provides a good balance between range and lift capability while being thick enough for manufacture. Here is how the performance compares between the airfoil we chose using the quantitative approach and the one found using the qualitative approach. Although there are thousands of airfoils, the most commonly used airfoils fall under a handful of series. Some popular airfoil series are NACA, Epler, Selig, Clark Y, and MH series. NACA airfoils are perhaps the most commonly known and used series. They were developed by NACA, the precursor to NASA, in the 1930s. They developed a way to parameterize specific airfoil shapes using just 4, 5, or 6 numbers. This way, they were able to study airfoil shapes more systematically, which is why NACA airfoils remain popular to this day. For example, NACA 4-digit airfoils are parameterized using 4 numbers. The first number represents the maximum camber of the airfoil as a percentage of the chord. The second represents where the maximum camber occurs along the chord. And the last two give the thickness of the airfoil as a percentage of the chord. For example, NACA 2408 has a 2% camber at 40% of the chord and an 8% maximum thickness. The Epler series of airfoils are also popular, known for their performance and versatility over a wide range of flight conditions, and are usually designed to provide high lift. Meanwhile, the Clark Y airfoil is a widely used general-purpose airfoil design characterized by its flat bottom, making it simple to construct, and is known for its good lift-to-drag ratio at lower speeds. Various modified versions of the Clark Y airfoil exist, tweaking its performance for specific uses, such as the Clark YH with increased performance, and the Clark YS which is optimized for lower Reynolds number operation. Let's look at some common airfoil sections depending on the aircraft type being designed. Acrobatic aircraft usually use symmetric airfoils, as these provide consistent flight characteristics in both upright and inverted flight maneuvers. The most popular options are the NACA 4-digit symmetric airfoils, such as the NACA Sanfor, which you would another one too. For vehicles needing high lift capacity and/or high aerodynamic efficiency, we need to look at non-symmetric and highly cambered airfoils, which have higher maximum lift coefficient and lift-to-drag ratios. Some common options here are the Epler 423, CH10 4813, Selig 1210, Selig 1223. Although these airfoils generate high lift efficiently, they also generate high drag, which will limit the maximum speed of the aircraft. For high-speed aircraft, we need to look at less cambered airfoils, which reduce the minimum drag coefficient, allowing the aircraft to reach higher top speeds. Examples are the Epler 220, MH32, MH18, and Selig 8052. Notice that these are subsonic airfoils. Aircraft flying at transonic speeds, or about 80% of the speed of sound or faster, need to use airfoils that are specialized for these conditions. For flying wings or other tailless designs, it is important to look for airfoils with low moment coefficient. As mentioned on the first video, the horizontal stabilizer of an aircraft works to cancel the pitch down moment generated by the wing airfoil. If the aircraft has no tail, then you must use an airfoil with low pitching moment. This is usually done through what is called airfoil reflex, which is when the trailing edge of the airfoil is bent upwards. This has a similar effect to the up pitch produced by the horizontal stabilizer, but built into the airfoil itself. Some popular options for reflexed airfoils are the MH60, MH82, MH92, Selig 5020, and the Epler 186. For general purpose aircraft, the Clark Y airfoil and its variants are a common choice. Other common general purpose airfoils are the NACA 4412 and NACA 2412. Finally, let's look at a few tools and resources that can help you find the optimal airfoil for your design. Airfoiltools.com is a freely accessible comprehensive online airfoil database. You can search among over 1,000 airfoil geometries and see predictions of their aerodynamic coefficients for a range of Reynolds numbers. The UIUC database is another freely available airfoil database from the University of Illinois. JavaFoil is a neat Java applet that lets you experiment with airfoil geometries and predict their performance. It is a good tool to experiment with airfoil designs and their performance. Xfoil is a freely available program by Métis that's perhaps the most popular tool for airfoil analysis. It can predict the aerodynamic coefficients based on the airfoil geometry. While Xfoil is a command line tool, XFLR5 adds a user interface to Xfoil, making it easier to use. XFLR5 also adds additional features like panel and vortice-based analysis of wings and airplane shapes. Finally, Simnit Designer is a web-based platform that offers powerful tools for drone design and airfoil selection. Its multidisciplinary physics engine allows you to predict the full performance of drone designs and how airfoil selection impacts this performance. Learn more at simnit.aero.
Thank you for joining me as we learned about airfoil selection for fixed-wing drones. I hope you found the video series interesting and informative. If you enjoyed it, please give it a thumbs up and subscribe to stay updated with our latest content.